So, good morning, everyone. Welcome to the first 2024 webinar for WWN. And we're really pleased to actually tackle a topic of great importance that I think will, stimulate some discussion and perhaps encourage some of you to move into that field. We are extremely grateful to have Dr. Carolina Ruiz.
Let me price code for you now. You can hear one key.
Hello.
Original.
Whoever has their, please mute yourself. Sorry about that. Dr. Ruiz comes to us from Worcester Polytechnic, where she is a professor of computer science and neuroscience. And she actually does a lot of work in artificial intelligence and machine learning. And she's going to tell us about how we could apply some of those, technologies for moving the neuroscience field. So again, I won't belabor the introduction, but I just want to say thank you in advance for your willingness to participate into this webinar. So Carolina, please, if you want to share your slides.
Thank you so much, Dr. Edwards. And I want to thank you, as well as Dr. King, for inviting me to give this presentation. I'm delighted to be here to talk about my favorite topic. And also I want to start by saying, Michaela, you have been amazing to work with. Thank you so much for all the help and the logistics and so on. So I'm delighted to be here and start sharing my screen.
Thank you.
So are you able to see my screen?
Yes.
Okay, perfect. So thank you for the introduction, Dr. Edwards. I have been at WPI working on artificial intelligence, in particular machine learning, and its applications to medicine and health. And today, during this webinar, I plan to do a very brief introduction to artificial intelligence. I think that given the fact that we come from different fields, it would be a good idea to provide a very perhaps superficial introduction to artificial intelligence, and then look at some of the synergies between artificial intelligence and neuroscience. And with that, let me start by the outline that I described a moment ago, looking at AI and its foundations, as well as some history and developments, different views of AI, the symbiosis between AI and neuroscience, some other success stories of AI outside of neuroscience, and some important considerations for us to take into consideration in AI. So let's start at the beginning. What's artificial intelligence? And then, even though I won't invite you to provide your input on this because it might take too long with a large group, I want you to take 30 seconds to think about what's artificial intelligence to you. Okay, so I hope that you thought about what is artificial intelligence to you, and we'll start looking into the field. Even though AI has become incredibly popular in the last year and a half or so, AI as a field of study started in the 1940s, and I'll walk you through some of that history. The name of artificial intelligence was coined by John McCarthy, who is a researcher at the Stanford University in 1956. And there are many definitions of AI. I'm sure that if I were to ask you what you thought AI is during those 30 seconds that I gave you to think about it, we will hear very different definitions of AI. And the truth is that it has happened in the field, that there are different perspectives in the field. And I'll walk you through all of them. But at the end of the day, kind of in its core, AI is an attempt to understand intelligent entities and to build them. If nothing else comes out of this talk today, I want you to remember this. AI is an attempt to understand intelligent entities and to build them. So in human history, there have been, there's like a lot of work in philosophy, in psychology, neuroscience, understanding intelligence. But what differentiates AI from other fields is that emphasis in building intelligence. So this is a definition that, even though, I mean, as I said, there are lots of different definitions in the field, then these two aspects are core. The understanding intelligence so that we can build intelligence, and the building of intelligence allows us to understand intelligence as well. So this comes from a famous textbook, kind of the Bible in the field, Rosalind Norvig textbook. And again, this definition only makes kind of explicit these aspects of AI. But now, if we want to understand intelligence and we want to build it, we have to start by defining what intelligence is. And again, throughout human history, we have been puzzled by that question: what's intelligence, right? And then there are many different definitions of intelligence, but the one that I will use here, because you will see it's relevant to AI, is this one. Is intelligence is the degree of accomplishment exhibited by a system when performing a task. So it's not intelligence in the general sense of being intelligent and being able to do everything, but it's intelligence in the context of a certain task that we want to perform. And it's that degree of accomplishment that the system exhibits performing that task, which, as you, I hope, see, becomes measurable. It becomes quantitative. We can have metrics to measure that degree of accomplishment. And that's what we do in AI. We implement or build intelligent systems that we can actually have metrics to measure how accomplished they are. Okay, so with that kind of under our belts, now let's see what are the essential aspects of artificial intelligence. So again, I'll ask you, if you were asked to build intelligence, what do you think that you will need to build intelligence? Let's think for 10 seconds. What's needed to build intelligence? Well, I hope that you kind of think that one important aspect of building intelligence is being able to represent knowledge. We need knowledge to function. So one important aspect in artificial intelligence is knowledge representation and what techniques we can use for doing that. And then once that we have knowledge, what do we want to do with that knowledge? Well, normally what we want to do with that knowledge is to solve problems, right? So we live in a world in which kind of one important aspect of intelligence is that ability to solve problems. So then another part of core AI is having problem-solving techniques that build upon that knowledge in order to solve real problems. Okay, so then if we have that as a core, then I will start describing the soft fields of AI. And these soft fields of AI have been inspired by human intelligence. Again, let's take a second to think why we think that we are intelligent. What makes us intelligent? Well, so we don't have time to go around asking your opinions, but I hope that some of you have thought about one thing that makes us intelligent is our ability to learn, right? We wouldn't call any entity intelligent if it's not able to learn. And definitely that's one major aspect of intelligence. And then machine learning is the subfield of AI that deals with learning. But also other aspects, I mean, learning is great, but then you need to apply it to real problems. And then another thing that makes us intelligent is that ability that we have to interact with the environment, right? How do we interact with the environment? Well, many things. One of the things that we need to do to interact with our environment is that ability to see the environment around us so that we can understand what is around us. If I'm looking at my screen and I see a lot of boxes in front of me, I realize, oh, I'm in a Zoom meeting, and then the camera is pointing at me, and then I know how to behave in this context, right? So then machine vision is the subfield of AI that deals with that, seeing the world around us and understanding the world so that we can interact with the environment. Okay, another area of interaction with the environment that is really central to human intelligence is our ability to communicate in a natural language, right? I am talking right now to you, and then you are listening to me, and then through that communication, we're able to actually share ideas. And then natural language processing is the area or the subfield of AI that deals with this interaction with the environment, namely communicating in a natural language. All right, so these are some of the aspects of intelligence and kind of core AI that are the central techniques that are central to all these subfields of AI. Let me talk a little bit more about each of these subfields. So let me start with machine learning. In machine learning, we work on writing computer programs that learn from experience to improve their performance on tasks. If you remember my first slide about artificial intelligence is creating or building intelligence in a way that we can measure the performance of that intelligence. And then machine learning deals with that, how we write computer programs that are able to learn from experience to perform better and better on tasks. While we have machine vision that deals with seeing, that ability to see, just like given either an image or a video, being able to understand what is contained, what objects are in that image, and what they mean together. And then in computer vision, we write computer programs to do that, understanding images and being able to classify images as well as do object recognition. And then natural language processing, again, is that subfield of AI that deals with writing computer programs that can communicate in a natural language. And by communicating, we mean either understanding natural language, so processing natural language to understand it, or generating it, or both, right? So those are the subfields of AI in a little bit more detail. All right, so let's see. Robotics is an area that brings them together. So it's not the only area that does, but then you have seen robots trying to learn to imitate human behavior, interacting with the environment and so on. And robotics really needs to deal with learning with vision so that robots are able to interact with the environment, and ideally as well, being able to communicate with humans in a natural language. All right, so let me talk a little bit about the evolution or the evolvement of AI, of the AI subfields. So all three AI subfields are based on the core AI techniques. So the core AI techniques are really what kind of support them, starting with knowledge representation techniques. And then there are lots of different fields that contribute towards that knowledge representation techniques. Data science, of course, in their storage and retrieval of knowledge, mathematics, logic, probability, and so on that provide frameworks to represent knowledge. And on top of those techniques, then we have problem-solving techniques that come mainly from computer science and algorithms, mathematics, optimization, modeling, and so on, that allow the use of this knowledge to solve real problems. And on top of this, then the three subfields of AI built upon to solve specific problems in each of these subfields. And then I'll walk you a little bit through the evolution of these subfields. So starting in the 1940s, then these fields have been growing quite a bit. But until the 2010s, they grew kind of separately from each other, all building upon the same core techniques, but really each one kind of focusing on either the learning, the vision, or the natural language processing. But then since the 2010s, we have had an explosion, a huge, oops, I went the wrong way, sorry. So the explosion went the wrong way. So there has been a huge advancement in techniques, in particular in machine learning. And this kind of huge kind of success in machine learning has really benefit as well machine vision and natural language processing. And this is not surprising, right? So in the same way that for humans, our ability to learn really is crucial to our ability to interact with the environment, the same thing happens in artificial intelligence. This explosion of of new techniques and so on in machine learning has really benefited machine vision and natural language processing, which continue to have their own objectives and their own work, but now built upon work in machine learning. And then now the three subfields are more interconnected than ever. So techniques from one of the subfields have been really kind of built upon the other ones, and there is a great connection now between the three subfields. All right, so not only that, but these techniques have become, or these subfields have become so sophisticated that now for machine learning, it's not only writing computer programs that are able to learn from experience, but now the learning has become so good that now they can also generate new data, new content. And similarly with machine vision, not only the algorithms are able to identify objects in images and videos and classify images, but they can also generate new images and new video. And the same thing with natural language processing. Now it's able to generate very well new text and new speech. So this is what we call generative AI. It's not only kind of classifying and so on, it's also being able to generate content. So for generative AI models overall, then is that I repeat the same thing, just is learning patterns and structures from input as we did before, but now it's able to generate new content that has similar statistical properties as the content that was used to train these models. And then one of the things that is important to keep in mind is that in order to do this, normally or usually generative AI models require a lot of data. They require a lot of training, a large training set in order to accomplish this level of performance. And then you might have heard in natural language generation in particular, we call these large language models. And it's called large language models only because these models require a lot of input to be able to really learn patterns so that they can generate new language with high performance. All right, so then I'm just like trying to provide a little bit of context as well as a little bit of terminology that I'm sure that you have heard about generative AI and machine learning and large language models and so on. Okay, so let me just go back and then let's look a little bit about the foundations of AI and different views of AI. So AI is a very interdisciplinary field. It's not created in the vacuum. It's really building upon a lot of the work that we have done in different fields. So let me start by remind you that AI is that attempt to understand intelligent entities and to build them. And then I was mentioning before, in AI, different researchers might have a different point of view about AI and different kind of emphasis in their work. So this is a kind of a really gross kind of classification across 2 dimensions, but it's a really useful one to have so that we understand kind of different perspectives in AI. So this classification is given in 2 dimensions. The first dimension is whether we're comparing intelligence in terms of human intelligence or whether we're thinking of intelligence as something that is not necessarily restricted to humans. So intelligence that we would call rational intelligence, that is not only unique to us, but it might be better than ours or different than ours. Okay, so that's one of the dimensions. The other dimension is whether for us intelligence is about thinking or is about acting. And that's different, right? So I might be very intelligent solving problems, but if you ask me for an explanation how I did it, I might not have one. I might not have kind of a reason, kind of a step-by-step description of what the logic I use to solve that problem. All right, I was thinking that perhaps for this group, a better word than acting is behavior, right? So we talk in terms of behavior that might or might not be having a rational description behind it, but it's just kind of the acting part. All right, so in AI, we have all these 4 big groups of approaches and different people see AI. according to more or less one of these approaches. And again, these approaches are based on not only AI, but then if you think about it, people in cognitive science, in neuroscience, in philosophy, in psychology, have been looking at this idea of how humans think. So trying to understand how that intelligence of thinking in humans comes through. And then for that, it requires a lot of introspection, thinking about how we think and how we solve problems and so on. So continuing with humans, then the other part is about acting, how we act, and what's the behavior that makes us intelligent. And psychology and neuroscience have clearly kind of focused on studying this type of intelligence. Now, not thinking about intelligence as a human property, but intelligence more globally, then rational thinking, then we have mathematical logic that looks at this. Philosophy for many, many centuries has been looking at how we rationally think and so on, and economics in terms of rational decision-making. And then for the acting rationally, then again, a lot of mathematics there, optimization, economics, control theory. So AI, to the point I'm hoping to convey here, is really kind of an interdisciplinary field that builds upon a lot of other fields, and also is not a unique way of looking at the world or intelligence, but it's just really a combination of all these different perspectives on intelligence. Okay, so then let me just once again kind of present here. So philosophy, mathematics, economics in the sense of formal theories for rational decision-making, neuroscience, psychology, data science, computer engineering, because it's really important to have computers when we implement intelligence to have high-performance computing so that problems can be solved within a reasonable amount of time. Control theory, because we want to do optimization, as well as linguistics. All these fields have contributed to AI and continue to contribute, and is really a close synergy with all these fields. Okay, I, as a computer scientist, realized that I don't have computer science explicitly here mentioned, but then algorithms and computer science is so central to AI that I didn't have it as a separate field here, but it's just like AI and computer science are really hand in hand. Okay, so let's move on from there to synergies between AI and neuroscience. And then I must confess to you that we could spend a year talking about this topic, or 2 years, or maybe a PhD studies, or maybe our whole career talking about this. So what I will try to describe to you in 10 minutes, of course, won't give any kind of deep coverage of these topics. Really, it's just try to provide you with a little bit of my own thinking about this, and kind of hopefully getting you interested in learning more about this. All right, so let me start by, okay, so I'll look just at this particular piece of neuroscience. Of course, in neuroscience, we deal with human intelligence. So I'm on this part of the whole spectrum. And then in neuroscience, I mean, is the behavior is some of the mechanistic thinking as well, but is mainly the behavior that I will be describing here. All right, so I'll start with neuroscience-inspired AI. And then I brought back this idea of understanding intelligence so that we can build it. And I have this human brain right in the middle for 2 reasons. And then I'll tell you the 2 reasons now, because otherwise I'll forget. I might forget at the end to tell you. The 2 reasons I have it there is because in neuroscience-inspired AI, then the human brain has been a big inspiration, trying to model the human brain. But also I want to make the point that all the developments that you will see in a moment have been the result of a lot of work and a lot of thinking by human beings. So the human brain was involved there to achieve all these developments that I will describe. And then what I'll do is that I'll try in about 5 minutes to walk you through 80 years of work in AI. So then it will be really dense and really compact, but it's just, and it's impossible to give kind of include everything here, but then I'll try my best. So then what I'll do is that I will give you 80 years of progress in this piece. In order to model the human brain, then we need to start at the beginning. We need to start simple. And then we need to start with just one neuron. So we need to start thinking about how we model the behavior of just one unit, one neuron. And then after that, worry about how the whole brain works, right? So that's exactly how it started in the 1940s. McCulloch from the University of Chicago, the University of Illinois, Chicago, and Pitts at MIT, they started looking at how to model the behavior of one neuron. And they created a mathematical model that is called the McCulloch-Pitts unit that really extracts mathematically the behavior of a neuron. And it's just like all these stimuli from the environment, how that's captured by the unit, how it uses an activation function to measure the aggregate, some of the inputs, and after that, then producing a response. And this is captured by this mathematical model of the one neuron. Of course, like in any mathematical modeling or any modeling for that purpose, then or for that matter, then the model really is an abstraction. It really ignores some of the things, but it does a good job capturing the behavior of a neuron. And then the idea, well, once that we have that, is now how do we make that one unit learn? What algorithms do we have? And then based on fairly old mathematics, a lot of calculus, the linear algebra and other math, then there was an algorithm that was described in order to train one neuron to learn. And then it turns out that that algorithm is really interesting. It's called the gradient descent algorithm, and it has become central to a lot of what we do in AI. Then that algorithm was also implemented. So Rosenbrand in Cornell University, he was crucial in actually taking not only what McCulloch and Pitts did in terms of describing this mathematical model, but actually implementing it and showing the capabilities of that one neuron, what it can learn. And in the 1960s, at the end of the 1960s, Minsky and Papert from MIT, and I'm sure that you have heard about them. And then let me just backtrack for a second, because this is a neuroscience group, and I forgot to mention that that McCulloch and Pitts, in addition to being mathematicians, they were cognitive scientists. I mean, so a lot of this work has been done by cognitive scientists and neuroscientists. Similarly to Rosenblatt, even though he did a lot of the work of implementation, he was a psychologist, a behavioral psychologist. And Minsky and Papert, you know, Minsky was a linguistics person, and then Papert also in cognitive psychology. They proved mathematically how much just a brain that contains one neuron can learn. So just one neuron is able to learn every linearly separable function, which is, there are a lot of functions that are linearly separable, and then a brain with just one neuron is able to learn all of those. But they also, of course, exposed the fact that one neuron is not enough. And we knew that, right? It's not a surprise. We know that our brain doesn't have just one neuron. We knew that we needed to have a network of these neurons. The problem is that at the time, there was no known algorithm that would be able to train a neural net of this type. Why? Because then, in general, in a problem, we have inputs, we know what the inputs are, and we know what the outputs should be, but we don't know the inner values that each of these hidden units inside the network needs to produce. The same way that for our brains, when we're learning something, we know what is given to us and we know what is the answer, but we don't know what each of the neurons and layers in our brain should be producing or doing in order to capture that behavior that we're trying to learn. Similarly here, there was no algorithm that would be able to, be used to do that until, and after much thinking, then people came up with that algorithm, again, based on a lot of math and algorithmic ideas. In the 1980s, the algorithm was produced. It's called the error backpropagation algorithm. And then in particular, a group of different researchers, and I am mentioning Hinton here. Hinton is one of the grandfathers of artificial intelligence, was involved in that work. Okay, and that's good. So with that algorithm, we were able to train artificial neural networks that had more than one neuron, and therefore being able to solve much larger problems. Well, that sounds all great. And then let me tell you that in my own career, then the idea at the end of during the 1980s and 1990s and the beginning of the 2000s, then the rule of thumb that we used when we work with this type of artificial neural network was to keep it shallow, to have only a couple of layers. So we were able to handle neural networks that have, say, 2 or 3 layers at most, because of the computational power that was needed in order to train them. It would be too expensive. It would take too long to train deeper networks or bigger networks. But then again, we knew our brains don't have 3 or 4 layers. Our brains have lots and lots of layers and millions of neurons. So then we knew that we needed to have deeper networks in order to be able to have higher performance. The bottleneck was having computers that were powerful enough to handle this, and algorithmic developments that were able to kind of make this efficient. So after a lot of work by a lot of smart people, then we were able to, and by we, I mean the whole field, of course, I'm not taking credit myself for this, but the credit of the field. We were able to work with really deep neural networks due to these advancements in computational power and really clever ideas that people had for algorithmic development, so that these networks can be trained. And still, training them, it may be a matter of days. But then if you think about it, as humans, we spend a lot of our formative years learning. So we spend, I don't know, the first 5 years of our lives learning a language and so on and so forth. So actually having a neural net that takes a few days being trained is not in comparison a big deal. Okay, so then there are lots of people who have worked on that. I'm just mentioning here in particular Benjo and Hinton and the Kuhn. They received, for this work that they have been doing, they received the Turing Award, which is the equivalent of the Nobel Prize in computer science. All right, and then since then, that was in the 2010s. Since then, or the 2010s, since then, there has been a huge proliferation of specialized deep learning networks and architectures for different purposes. Some are more focused on the natural language processing, some are more focused on the machine vision aspects, some are more for classification, some and so on. But then this proliferation has really kind of produced the explosion that we have had in the field. It's impossible nowadays to keep up with all these developments, because it's just lots of smart people around the world working on these problems and producing new ideas constantly. So it has been great. And in my mind, one of the important developments most recently has been the one in which now we are looking in artificial intelligence to interpret the inner workings of these deep learning networks. So we have been looking at these networks now, not only as a way for them to give an input, produce the right output, or have the behavior that we want, but now we have been really interested in looking at the inner works of these networks and trying to identify the behavior or what these internal or hidden neurons are learning. What is the knowledge that is represented in them so that they can solve the problem at hand? And then it turns out that actually these networks behave very similarly to the brain. I'm using here an example of a deep network that deals with image understanding. So it's trained with images. And it turns out that as you go deeply into these, into the layers, then it's exhibiting the same behavior of our visual cortex, namely that kind of the shallow layers are capturing gross features of the images that we see. And as we go deeper into the layers, then those features are combined into actually more clear definitions of the different objects in the image. This is perhaps too small for you to see, but that's kind of the behavior that they exhibit, and is the same behavior that people have identified in our visual cortex, which in my mind closes the circle here, closes the loop in terms of understanding intelligence and building it, that allows us to, once that we build intelligence, help us understand intelligence as well. Okay, so now I have kind of gone, as I said, 80 years of history condensed into 5 minutes. And of course, this is just looking at this particular aspect of artificial intelligence. It's not everything that has happened in artificial intelligence, but this has been kind of a huge explosion in terms of the performance of these artificial neural networks. Now let me look at the other side of the coin. Let me look at AI in neuroscience. And here, again, we could spend a whole year looking at or more of applications of AI in neuroscience and how AI can help in neuroscience. I am showing just a few examples of that, some kind of typical examples of applications of AI. In particular, for example, AI applied to brain-computer interfaces or brain-device interfaces, a lot of work in that field. And I'm mentioning here work done at WPI and elsewhere as well. AI in the study of the connect tone, also very important. So a lot of work, both in terms of analysis and simulations. Also work in analysis of neuroimages, using AI to study the aging of the human brain, which is kind of a really important and aspect of neuroscience, looking at our brain and how it evolves and how it ages. Using AI for the study of neurological disorders, a lot of different examples applied to tumors. The example I have here is autism spectrum disorder, stroke, a lot of different aspects that has been a lot of research in neuroscience in which AI has been helping, and also the use of AI in large-scale biomolecular simulations in different research labs, looking at how we go from genome and simulation of the genome to simulation of our nerve system and so on. Okay, this is a very short description. Again, this is worth having one or more talks on this topic that just I wouldn't have the time to cover here. And then I try to have representative examples here, but I'm sure that I missed your favorite one. And then thinking about which one would be your favorite ones, I figure it's just easier for me to show you my favorite ones, because then this is like it will be a lot easier. So I'll show you 2 of my favorite examples that come from my own research. And then, as I mentioned at the beginning, I work on AI and machine learning applied to medicine and health. And then the 2 examples I want to show you are, one of my main areas of research is sleep medicine, using AI in sleep medicine. Sleep is an incredibly important physical and behavioral function that is essential for our physical and our mental health. And then I have been lucky enough to be studying and working with experts in sleep for many years and using AI and machine learning in this field. And I have been looking at both the physiological aspects as well as the behavioral aspects of sleep. I'll mention first behavior. So together with collaborators and students at WPI, I have been working on understanding sleep behavior and using AI to generate tools that enable and kind of encourage better sleep behavior, because sleep behavior is really important for mental health and for physical health. I have been also working on physiological aspects of sleep, looking at body responses and behaviors during sleep, looking from brain activity as breathing, heart rates, all sort of muscle activity and so on during sleep, and using deep learning in order to capture patterns in that behavior so that it allows us, for example, one of the examples is classifying sleep stages. We have at WPI, my group and my collaborators, we have achieved the highest performance in doing this type of prediction of what sleep stage a person is during sleep. And more importantly, we have been focusing on understanding, interpreting these neural networks that we have constructed. And similar to what I showed you before about the visual cortex, we have identified that the deep learning networks that we have created that are very good at classifying, they're also very good at capturing by themselves without being trained to do this, capturing events in the signals, events in brain activity, say spindles and K complexes and so on and so forth, that they weren't trained to do, but then they kind of emerging behavior that is similar to the knowledge that sleep experts use in order to classify sleep. Okay, and the other big domain I'm working on is pain medicine. Pain medicine is a fascinating field, and there are lots of interconnections between sleep and pain. And I'm working on this research together with Dr. Jean King and a large group of faculty at WPI, as well as the University of Massachusetts Medical School and Boston University Medical School and Harvard University Medical School. We have been looking at how we use machine learning models to be able to identify who will respond well to non-pharmacological pain treatments. So trying to identify biopsychosocial markers that will allow us to predict who will react well to pain treatment, and what markers we can identify that allow us to monitor that progression during treatment. And this is a fascinating field because then it will allow then medical doctors to have a decision system so that they know which patients, with which pain patients to prescribe these treatments. In particular, we have been working with mindfulness and acupuncture and knowing in advance who will be likely react to these treatments. And then in that way, saving both the patient's time and a healthcare cost by being able to have this precision medicine approach. Okay, again, I'd be happy to talk about this for hours and hours because we are doing really interesting work in all these fields, and these fields are at the intersection of AI and neuroscience. But in the interest of time, I will continue, and then I will just kind of remind you that what I have covered here is just a small piece of the whole AI field. And then, of course, I didn't even cover all the interactions between neuroscience and computers and artificial intelligence. It's just kind of a big overview for now. All right, so that there is a lot more to look at and a lot more to describe, a lot of different techniques that exist in AI. And what I'll do is that I'll give you a very brief kind of display of other huge success stories of AI in everyday life. They are not related necessarily directly to neuroscience, but they are things that are part of our lives. And what I'll do is that I'll walk you through time again, so that you see that these are not things that happen in the last year and a half. It hasn't been ChatGPT only, but lots of successes of AI throughout the time. Okay, so a lot of work has been gone from natural language processing, that idea of being able to communicate in a natural language, into personal assistance. So their behavior is not perfect yet, but they have become really good at understanding language and being helpful at different tasks. Google Maps, for example, or Apple Maps, any GPS system that you use is artificial intelligence. That idea of being in a situation that you need to go from point A to point B and having lots of possibilities of get this constraint satisfaction problem that we have, this idea of finding routes, is an AI problem. And then I hope that, like me, you have been relying on this type of technique nowadays more than ever before to find our ways around, especially in places that we don't know. Recommendation systems have been around for a long time, and then learning your taste or your preferences to provide recommendations. A lot of interest in these areas that are commercial interests that have pushed forward the research as well, for good or for bad. Now, face recognition has been improving quite a bit, all this work on machine vision. And then we have had these systems around with very good performance since the 2010s. Another huge success, totally different application, is game playing. So I do remember in 1997 when actually the first computer chess program was able to win again a grandmaster. That was a big success. Chess is a really complicated game, and then people thought that that wouldn't be possible, and it happens. I do remember going to an AI conference when the people from IBM were awarded this big award for this achievement. You might have seen IBM Watson winning Jeopardy, which was a big success. Again, a lot of work on knowledge representation to be able to quickly be able to answer questions there. And perhaps a more impressive accomplishment was a Go player winning again a world champion, because Go is a game that is even more complicated than chess, and being able to win here was a huge, huge accomplishment for AI. And as you can see, these have been throughout time, not necessarily in the last couple of years. Now, I put together two things in one slide for being more efficient, but then AI systems have been helping in mathematics to help mathematicians prove theorems, which is important. They have been around. That's what I did for my undergraduate thesis, working on one of these theorem prover systems in AI. Medical diagnosis, also a really important area. So AI have been helping in oncology, in lots of different fields in medicine. Now, another area of kind of really a lot of work has been in autonomous vehicles. Not quite a success story yet. Lots of work that has gone into that field. Autonomous cars are not kind of ready for prime time quite yet, but then a lot of work towards this aim has really triggered really good work in deep learning. All right. Space exploration, a lot of work in AI for having robots that are able to go to outside outside Earth. In particular, there have been a lot of work sending these robots to Mars and exploring autonomously a new, totally different environment. Now, a lot of work on image classification and object recognition that is just really amazing. The ability that now we have with deep networks to provide an image to a network, and the network being able to not only identify the objects that are in the image, but being able to actually provide a textual description of what is contained in there. Not always we get perfect answers to that, but then it has become extremely sophisticated. So again, this has been work that has been happening in the 2010s and the 2020s. Now, perhaps more known to everybody is the appearance of these really systems based on large language models that are generative AI. In particular, OpenAI created ChatGPT and made it public, and that helped with explosion in the sense of people knowing about AI, and really AI became a household term now with the OpenAI making ChatGPT so available to everybody. Now, every large company has a similar system. Google had BART, and now they renamed BART Gemini, and then again, trying to achieve the same type of performance. All right, and then I wanted to show you this particular one. This came 6 days ago. This is off the press right now. It's just fresh out of the for the news. This new system is OpenAI, again, producing this system that is called Sora. And I want to give you, in a second, I want to give you a short sample of that, because I think that is quite impressive. And I want you to, as I said, this is really new. I want you to see it. The idea here for this, are you able to see the page with the, okay. Then Sora, what it is Sora is that you can give it a text, a text prompt, and then it will produce a 60-second video that represents that prompt. So I want to show you some examples on their page. So I want to show you this in particular. So the prompt was: a stylish woman walks down a Tokyo street filled with warm, glowing neon and animated signage. And she's wearing a black leather jacket. So that was the prompt. And then look at the type of video that these generative AI networks are able to produce. I think that, I mean, just quite impressive, the type of realistic videos that we can achieve, and realistic images and so on. And similar behavior is obtained by ChatGPT in terms of producing text and so on. This one in particular, Sora, is about producing images and video. All right, there are many more examples on the page that I think that are worth taking a look, but in the interest of time, I'll stop there. And if you're interested, then you can visit their website. All right, and then I just want to conclude by saying that there are important considerations that we need to make when we are talking about building intelligence. Of course, there is a lot of ethical aspects of AI that are very important to consider. We, of course, want to work in responsible AI, respecting privacy and having security, having always a human in the loop for the development of these systems, as well as kind of our intention is always to create AI that will be good for everybody, that will be available to everybody and good for everybody. Again, this is a huge topic, and we could spend a long time speaking about this. But at the end, I want to kind of share with you this. Perhaps this is what people think that AI programmers do, right? All this magic that happens. But in reality, do you know what AI programmers do? So what we do is this. We really spend a lot of time thinking about how to improve our performance, how to do better knowledge representation, how to have better and faster problem-solving techniques. It's a lot of work, but I think that has been work that is very worthwhile and will continue to impact society forever. Okay, and then with that, I want to, again, thank you, and I don't know if we have any time for questions.
Thank you so much, Carolina. You've given us a lot to think about. There might be some questions, but I think, let me just ask you just one that I didn't hear you talk about. You talk about building intelligence and all that, but can you say something about emotional intelligence and in the context of interactive AI?
Oh my God, thank you for asking that question. Oh, there is so much to cover in AI. Emotional intelligence and emotional AI. There is a lot of work at MIT working on this type of approaches. Yes. So lot of topics to talk about, whether these systems are self-conscious or not, whether there is emotion. And there is, for example, there are work in creating visual characters that help people through problems, right? For example, like healthcare and visual healthcare or no, visual caregivers. And then the idea that they can interact with a real person and convey a sense of emotion, of understanding what the other person is going through, really is important for the communication to work well. So a huge area of study. Thank you for asking that.
Thanks. Other questions?
So again, Dr. Ruiz, thank you so much for this. This was a great presentation, and I love that you got us on the space of having a conversation about what is AI and how it relates to neuroscience. Thank you for doing that. One of the things I love, and I know you talked about because we're working together on this, is using it to predict. I mean, I think in a lot of ways, the ability to predict something is not something that we're really good at in doing in many ways, and using models to predict. So what do you think about how that's going to change what we do and how we think, especially in health?
Oh, absolutely, absolutely. So a big piece of all these models, especially the machine learning models, is prediction, right? It's looking into the future. And that's central for humanity. We have always, I mean, we might not be so good, but we're becoming good. We know, or people learn there's seasons, and then the winter will come, and you have to prepare for the winter. So you start projecting into the future and predicting. And these machine learning models are very good at doing that. They're trained to find patterns in things that have happened in the past so that they are able to predict the future, and that's central. That's really an important aspect of intelligence. Completely agree with you.
Carolina, thank you so much. I'm going to have to jump off. I have a 10 o'clock. So thank you from the bottom of our heart. But if there are other questions, I don't know if you have time to stay for a couple of minutes.
I can stay for a couple of minutes. If people want to ask questions, I'll be very happy to stay. Yeah, thank you. But at the same time, I understand if people need to leave, I totally understand.
Okay, bye-bye. Thank you.
Bye, thank you, Dr.
It looks like Martha has a question. Professor Davila Garcia.
Yes, thank you so much for this fantastic journey through AI and neuroscience. It was really, really very intriguing in a lot of ways. Also, because we have a lot of students in the audience, I was wondering if you could actually just tell us, what does it take to actually get into AI? Because I'm guessing that you have to have a very strong computer background. Can you actually jump from being a neuroscientist to learning then the amount of mathematics that and the amount of knowledge that you need to become a computer expert to be able to navigate through those through both of those fields easily? I think a lot of our audience is primarily neuroscientists, and I'm just wondering, many of them are going to ask, what do I need to get, what kind of skills do I need in order to jump now into AI?
Yes, thank you. That's an amazing question. Thank you. Yes, AI, as I was showing you, all these areas that really fit into AI and are synergistic with AI. I focus only on neuroscience because of this audience. But then we need not only kind of the algorithmic expertise and the mathematical expertise in order to create these techniques, these problem-solving techniques. We need the domain expertise to work on the important problems and understand the behavior of the models, say, in the context of the application domain. So we need the domain expertise that comes from neuroscience and from all these different areas. Now, in terms of preparation to jump into AI, I agree that actually all this thinking about the biology and in neuroscience, the biology and the psychology and so on and so forth prepares you well to understand the behavior of these models. So I invite you, and if you are interested in the field, by all means, join us. There is always useful to know mathematics, from probability to linear algebra to calculus. All these areas are really important. but it's not constrained. If you don't have those, doesn't mean that then you cannot get into the area. In some cases, I mean, just certain methods use certain type of mathematics that you could pick up and learn, but then with experience, it will become easier. So I would say, yes, I mean, the idea is that in AI we want to build, so then having some at least basic programming experience will be important. So I invite you, and then it's not only for AI, but for really kind of the future. We all need to learn a little bit about how to program, and it doesn't mean that it has to be basic programming. There are tools on which you can program that will simplify things. But it's important to kind of have this algorithmic thinking, this anticipatory ability to write instructions and being able to know what will happen with those.
Thank you.
Great answer.